In Module 1.4, we will go over mathematical backgrounds that are necessary for multi-scale modeling techniques. I understand some of you might be more familiar than others. However, it is important that we still go over these terminologies so that everyone has a strong mathematical foundation. The topics we are gonna cover is differential equations, both ordinary and partial differential equations, linear algebra, matrix theory, and tensor calculus, numerical methods for differentiation and integration, statistics and probability, descriptive stats and basics of probability, Fourier analysis for Fourier transform and inverse transform, dimensional analysis, optimization techniques such as linear and nonlinear optimization, genetic algorithms, and machine learning techniques. Now let's start with ordinary differential equations. An ordinary differential equation is an equation that contains one or more function of one independent variable and its derivatives. So for example, you can consider y as a dependent variable and t as an independent variable. So if you have a function which has both t, y, and its derivatives, such as first derivative y tilde, y double derivative, which is the second derivative, or its nth derivative, and equate it to 0, that will be ODE, or ordinary differential equations. ODEs are utilized in mechanical engineering to model systems where the rate of a change of one or more variable is central to the system's behavior, such as mass spring damper systems. So if we consider this equation where m is the mass, x double dot is the double derivatives, c is the damping coefficient with x dot as the first derivative, k is a spring constant, x is a displacement, then you can consider ft as an external force, and from that, if you solve it, you can calculate the displacement over time. Now, this model is a fundamental in vibrational analysis and automotive suspension and dynamical control systems. Now, how do we solve it? You can solve it analytically if you know actual impression and if you want to have indefinite integrals, but usually in engineering application, these are solved numerically, such as Runge-Kutta methods, power series method, and so on. Now, while this was the case of the single variable, we might have multiple variable such as x, y, z, and so on. So these are called partial derivatives. So in this equation, we have the x, the y, the actual variables, and the u, and then we have u x, ui, uxx two derivative, uxy two derivative with x and y, and so on. A PDE is vital in modeling dynamical mechanical systems where changes occur over space and time. So for example, if you have single dimension or a line, we can have x. Now you can have two dimensions, such as x and y, that is a plane, or you can have x, y, z, that's the volume. Now, some of the examples for these PDE applications are heat equation to model the distribution and flow of heat of a material, where T is a temperature, alpha is a thermal diffusivity particular to that material, which we can calculate from, for example, ab initio methods or quantum mechanical methods, or some other classical methods as well. And Q represents the heat source. So del T is the derivative, alpha is the thermal diffusivity, and this is a Laplacian, or it's two second derivatives of temperature plus the Q, which is the represent the heat source. Another application could be Navier-Stokes equation to describe the motion of fluid substance like air, water, density, and what we need is density, velocity, and so on. This is especially useful for computational fluid dynamics. So here in this example, we have V is the velocity. It can be a vector, and it's a derivative and double derivative, and so on. How do you solve this? There are many methods to solve this. One of the most popular is the finite difference, finite element, and finite volume methods. Or you can have Fourier series analysis, especially if there doesn't have any nonlinear terms in it. So it might be useful for Fourier series analysis. But usually finite difference or finite element, finite volume methods are more popular. Now let's start with matrix theory and matrix concepts. So a matrix can be considered as a rectangular array of elements, typically numbers, arranged in rows and columns. A vector is a special type of matrix with only one row or one column. We'll show the example of that very soon. Now, what are the operations that we can do with these matrices? We can have addition, subtraction, multiplication, scalar multiplication. However, it's important that they follow specific rules for matrices. So for example, if we have 3 rows and 3 columns in a matrix, and another matrix is 5 row and 5 column, you cannot add them because their dimension do not match. If you want to add them or subtract them, so on, you have to pair them with 0, for example, to make them dimensional compatibility. Now, an important characteristic of a matrix is determinant, which is a square matrix. So what I mean by that is the number of rows and the number of columns has to be the same, and it's crucial for determining the solvability of a system of linear equations. Another important concept is the inverse of a matrix A, which is another matrix of the same size denoted by A inverse, such that the A multiplied by A inverse is identical matrix. So you can imagine you have 5 multiplied by 1 over 5 is 1, but here because we have multiple elements, we have 5 by 5 matrix multiplied by another 5 by 5 matrix, leading to I, which is the identity matrix. A inverse exists only for square matrix where the determinant value is 0. Now, very important concept are eigenvalues and eigenvectors. An eigenvalue is a scalar, lambda, and its eigenvector is a non-zero vector, v, such that v is multiplied by matrix A, product is the same as v scaling it by lambda, or in other words, AV is lambda v. So you can represent A matrix as lambda v. So this is especially useful where you have to get the eigenvalues, or which are the basically diagonal components of a matrix, and others are zeros, for example. So this can be solved using some of the most popular techniques for solving matrix algebra is the spectral decomposition, LU decomposition, and so on. Luckily, these are already implemented in well-known libraries such as NumPy, SciPy, LAPACK, and so on. So we don't have to implement this from scratch. So, and there are many other models to solve sparse matrices and so on, which we'll talk about. So these applications of the matrix theory. So here's an example of a matrix where A11, A12, A13, A1M can be considered as a row vector. Similarly, A21 is another row vector. Similarly, A11, A21, A31, AN1 is a column vector. And these are similarly A12 to AN2 is a column vector. So as you can see, a matrix composed of row and column vector elements. Now, N and M could be same, so it can be 5, 5, or it can be different, so 3 and 5. So a determinant would have same number of elements, so 5 and 5, for example. These are useful for structural analysis, such as finite element method. So this is very popular for continuum mechanics, where you use matrices to represent the stiffness of the components and overall structure. The global stiffness matrix, which we can calculate from DFT or MD methods, K is assembled and or from experiment and solved using Kx equals to F. So X is a displacement vector, F is a force vector, and so on. Vibrational analysis, such as from modal analysis, if you want to get eigenvalues and eigenvector of a system that are useful for getting their natural frequency or natural modes. So you want to solve their another Kx equals to F type of equation, but here in addition we have K minus omega square M. Omega is the natural frequency or natural mode, and M is the mass of the system or particle. Or it can have dynamics or control systems such as state space representation, which uses the matrices for dynamical system in a state space of X given by AX plus BU. A is a system, B is the input matrix, and X is the state vector, and U is the input vector. Or it can be also useful for thermal analysis. Very important, because when we want to solve the conduction in material, that can be modeled using matrices, and especially when it's multidimensional, such as 2D or 3D, we want to have thermal conductivity matrix, which is XX, XY, XZ, and so on, and solve this for K lambda T, where lambda is the temperature difference or temperature gradient, in other words, and Q is the heat source. So basically, you want to capture how the heat will flow from high heat volume to low heat volume using an equation and a thermal conductivity. So now let's move to tensor theory and concepts. So we learned about vectors and matrices, and that's not it. So we can go beyond them, and tensor can be considered as a generalized mathematical object that encapsulates scalar, which is 0th order tensors, or vectors, which is a 1st order tensor, or matrices, which is 2nd order tensors. tensors of high order can thought of as a multi-dimensional arrays of numbers. Now, when we say rank and order, by that we mean the tensor is a number of indices required to uniquely identify each component of a tensor. For example, a scalar like 5 or 7 has a rank of 0. A vector, such as an array of 5, 7, 9, 10, is a rank 1. Similarly, a 5 by 5 or 2 by 2 matrix has rank 2. Another important concept is covariant, contravariant, and mixed tensors. Tensors can be classified based on how their components transform under a change of coordinates. So covariant tensors change similar to the coordinate differential denoted by the subscripts, while contravariant tensors change inversely to the coordinate systems denoted by the superscripts. Example of tensors are stress and strain tensors. So in mathematical modeling of mechanical systems, it's important to know about Hooke's law especially for anisotropic materials, where the response of a strain are different in different directions. So that's what we call anisotropic materials. And there we have sigma, which is the stress tensor. So you can consider I and j as 0, 1, 2, and j also 0, 1, 2, representing x, y, z dimension. So if you apply a stress, for example, in x direction or y direction or z direction, and or xx, which is in x direction only, or xy direction in the xy plane, and so on. And we have epsilon, which is the strain in KL direction, which is also varies from 0, 1, 2 for XYZ direction. We can consider a tensor Cij as well as function of KL, where C is the fourth order elasticity center tensor, which we'll try to calculate using DFT in one of the exercises. Now, another example is thermal expansion tensors. These tensors describe how material expand or contract with subject to temperature changes. Now, some of the important concepts numerically are integration and differentiation. During numerical integration, it involves in estimating the value of a definite integral when an analytical solution is cumbersome or function is known only at certain points, such as an experimental data. So some of the core rules that are used for numerical integration, and they are not just limited to this, are trapezoidal rules, such as which calculates the area under the curve as series of trapezoids, where h is the interval or the width, and b minus a is the extrema, so maxima and minima. So you can take the function, so sine x, for example, you can calculate the integral at sine at point of 0 and sine at pi 2, and sum them, and then multiply the interval and divide by 2. That will be the trapezoidal rule. Simpson's rule provide a higher accuracy by approximating the function such as sine x with a quadratic polynomial through 3 points. So sine x is a good function, we could actually guess it, but for some very complicated function, this might not be the case, and that's why we need to kind of approximate it with a polynomial function. So here we have a function of the value of a function at point A, function of at B, and then A plus B over 2, and then we have H over 3. Some of the examples for numerical integration are for structural analysis and fluid mechanics. Suppose you want to calculate the load distribution, which we'll try to simulate in the next module. Suppose you want to calculate the load distribution over beams and frames where the load may not be uniform or analytically definable. Then we need numerical integration. Similarly, if you want to evaluate forces and energy in a fluid dynamics, such as determining the work done by varying pressure force in a piston, we need numerical integration. Now, numerical differentiation can be considered as the opposite of numerical integration. So in this one, we want to have derivative of a function based on discrete data points. It can be based on forward difference, central difference, higher order, and then we need higher order derivatives. So what is the forward difference? Suppose you have point x. So you can take the value of the function at x and then 1 plus h. So h is the interval, and then you can calculate the first order derivative using fx plus h minus fx and divided by the h. So for example, h could be 0.01, and you have sine function, and you will calculate the function at sine, suppose pi over 2 plus 0.01 and minus function sine x over pi over 2 and divide by 0.01. So that will give you the first order derivative. Similarly, there could be central difference, such as x plus h, x minus h divided by 2h. So these are the cases of first order derivative. The same idea applies for higher order derivative denoted by f double tilde or double dash. So some of the examples of these numerical differentiations are motion analysis, so determining the velocity of a vehicle or machinery component from position time data collected by a sensor, for example, or for material science, such as calculating strain rates from experimental measured strain data in material testing. Now let's move to stats. Some of the key things we need to learn in stats are the measure of central tendency, for example. So central tendency describes the center of data. So when you say center, what does it actually mean? It might mean different things based on what we define as a center. So it might be mean, it might be median, or it may be mode. So what are these? So median is the sum of all data point divided by the number of data. So if you have 2, 3, 5, 7, 11, you can sum them divide by the total number of elements. It can give you the mean, or you can have median. So especially for can be considered as the middle value of the data set. So if you have 2, 3, 5, 7, 11, the middle value is 5, so the median is 5. But what if we have even number of elements? So in that case, you can take the from the middle the one ahead and one back of the middle value, and then take a average of that. That will be the median value. Now mode is interesting because it's basically the most frequent data. So if you have 1, 2, 2, 3, 4, the mode is 2 because it appears more frequently. Now that was the measure of central tendency. Now let's move to measure of dispersion. Now when it's a dispersion or variability, it basically measures how the data spread over the data sets. So for example, one of the concepts is variance, which is defined here by this equation. Variance given denoted by S square is a sum over xi, so I is the data point, minus x bar, which is the mean of the value squared for each data point, divided by the total number of elements minus 1. So to give an example, if you have 2, 3, 5, 7, 11 with mean of 5.6, you can consider S square with 2 minus 5.6 square plus 3 minus 5.6 square, so on, divided by the n minus 1, which is 4. So that will be S square. Now standard deviation is just a square root of the variance. So that will be 11.3 power 1.5, sorry, over 1 power 1 over 2. That is 0.5, that will give you 3.36. Range is the difference between largest and smallest value of the data set. Now we move to probability theory. A probability theory is basically a measure of how the likelihood of an event might occur. So it is quantified as a number between 0 to 1 or maybe 0 to 100%, which is kind of same thing. And 0 indicates impossibility and 1 indicates certainty. So a random variable is a variable whose possible values are numerical outcome of a random phenomenon. For example, strength of a material component subject to random stress, or flipping a coin, and so on. Now, probability distribution is very important for some of the mechanical engineering applications, which describes how probabilities are distributed over the value of random variable. Common distribution include normal, binomial, and Poisson distributions. Expected value. When we have a probability distribution, the long run average value repetition of experiment, it represents the expected value. For a discrete random variable, the expected value is calculated as xi, where the xi are the values, pi are its probabilities, and multiply and sum, and that will give you the expected value. Now, variance and standard deviation for a probability is the measures of the spread or dispersion or of probability distribution. So variance is expression of the square derivation of a random variable from its mean, and standard deviation is square root of the variance. Now, while these concepts could look very subjective, when we actually apply it for mechanical engineering application, it might be more tangible. Some of the examples include reliability engineering. So if a failure rate is lambda, the probability that the bearing, for example, survives beyond a certain time t without failing can be modeled using exponential distribution p. T greater than t is e minus lambda t, so exponential decay. Similarly, for quality control and Six Sigma, probability could be useful. Now we move to Fourier analysis. So Fourier analysis is a mathematical tool derived by the mathematician Fourier. So it basically decomposes a function into its constituent frequencies. And it's very useful because in the fields where the signals or functions are examined in the frequency domain, such as signal processing or a heat transfer or mechanical vibration, is very useful to break down the complicated equation into smaller parts in a way. So a Fourier series, it represents a periodic function as a sum of sine and cosine function. It is primarily used for function defined on an interval which repeat outside this interval, where suppose if we have a function fx with a0, an cos is a periodic function and sine is a periodic function, and with a and b and other Fourier coefficients calculated by the integral of the product with sine and cosine function over the period of f, where f is a period. Now, Fourier transform is extends the idea of Fourier analysis to non-periodic function. What if my function is not periodic? So it represents them as an integral of sine and cosine over the entire real line. Inverse is just as the sounds allows a reconstruction of a function from its frequency spectrum. So two common example of Fourier analysis is the vibrational analysis, determining the vibrational mode of a mechanical system, such as a car engine or a building during an earthquake, to understand how different frequency affect the system, or during heat transfer, such as solving a heat equation problem, such as temperature variation in a material. Now, from engineering application, it's very important to learn about dimensional analysis. So dimensional analysis is a mathematical method to reduce the complexity of physical phenomena by identifying fundamental relationship between variables solely based on their units. So dimensional and units. So when we say dimensions, it means physical quantities such as length, L, mass, m, and time, t, and so on. And there are other primary dimensions such as mass, length, time, temperature, electric current, and so on. So any physical variable in a way can be decomposed into these fundamental or primary dimensions. So dimensional analysis involves checking the consistency and formulating a relationship between these quantities. Now, we talk about dimensional homogeneity. So all terms in a physical equation must have the same dimension, ensuring the equation is dimensionally consistent. So this is kind of a check that we can perform to make sure our equation kind of makes sense when we solve these equations using numerical techniques. This principle is crucial for equation to be physically meaningful across different measurement systems, whether it's CGS system, FPS system, MKS system, in units, doesn't matter. So, for example, force has a dimension of mass, time, acceleration by Newton's second law, mass and acceleration, which can be derived into fundamental or primary dimension of mass, length, and time. So we want to be consistent when we solve the Newton's equation numerically and so on. Now, another very fundamental and very useful for modeling technique is the optimization. So in optimization, techniques are vital for enhancing performance, reducing cost, improving efficiency. They range from classical methods such as linear programming or nonlinear optimization to more modern approaches such as genetic algorithm and recently machine learning. So we won't have time to go over details of all these techniques, but here the idea is to introduce them to you. So such as linear programming involves maximizing or minimizing a linear objective function subject to linear equality or and inequality constraints. So some of the methods are simplex, dual simplex, and so on. They are used for supply chain management, manufacturing, and so on. Similarly, nonlinear optimization deals with optimization and objective function with at least one nonlinear constraint or nonlinear objective function. Luckily or unluckily, most of the optimization functions are nonlinear. So that's why we have to learn about gradient descent, ascent, Newton's method, and quasi-Newton method. Especially gradient descent is a very popular technique. So mechanical design is used for different applications as a mechanical design, where the idea is optimizing design parameters like shape and size of components for performance, such as maximizing stress, concentration, or maximizing the fatigue life. Energy systems, we want to optimize parameters in a power plant, for example, to enhance efficiency while reducing emissions. So another concepts that are important for optimization is genetic algorithm and the recently popular machine learning. So in a genetic algorithm is, as it sounds, we have the idea of the survival of the fittest kind of idea, and it's a base of evolutionary algorithm that mimics the process of natural selection involving selection, crossover, and mutation. So suppose you have the parents elements, you kind of made them, cross over them and mutate them and let it evolve them to get the final parameters or final variables that are needed for getting the ground state or the optimized variables. Another important techniques is the machine learning, which involves training the models on data to make prediction or decision effectively, optimizing an error function. So the error function or loss function are very important in machine learning. Now, there could be different type of machine learning, supervised or unsupervised machine learning. So the supervised machine learning is where the data is all labeled, so X and Y is well defined. Or unsupervised learning, it can have unlabeled data. So for supervised machine learning, you can have different methods such as regression, classification. So regression is where predictive model that can optimize continuous or categorical outcome based on input features. So if you have, for example, 0 and 1, that's like classification. While if you want to predict 0, 0.1, 0.5, these float values, for example, these are regression analysis. Now, deep learning has recently been popular in mechanical engineering applications, which involves complex neural networks that can model highly nonlinear principles. So most of the time, the data we work with doesn't follow a particular set of equations. So in that case, we basically try to establish the relationship between input and output using a combination of neural network functions, and we may not know exact mathematical function, but we'll be able to solve it. So the application of these techniques are predictive maintenance. Machine learning models can predict the equipment failures from sensor data, optimizing maintenance schedules and reducing our downtime. Or similarly for material science, especially, it has become very popular, and a lot of big companies are jumping into this, such as optimizing material properties prediction based on the composition and structure and processing parameters that we learned in the previous module. So based on structure and processing performance, we can predict the properties and performance and so on. That's it for this module.